All right, let's say we have two goods, good one and good two. And people are going to have opinions about their consumption of good one and good two. So, we might prefer to have one of good one and say 0 of good two to 0 of good one and 1 of good two. And that's how we might write that out, where this sort of squiggly version of a greater than or equal sign indicates that we prefer one to the other. And we might say that's sort of a strictly preferred, just like a kind of greater than without that line underneath. But we could also say weakly prefers, which we would write like that. We weakly prefer to have 1 of good one and 0 of good two over the opposite, right? And so typically in consumer theory, we'll assume that people have a complete set of preferences, meaning that they can kind of have this ranking of every possible combination of good one and good two, and they'll have an opinion over them. And if you were to look in any kind of microeconomics book, you'd see a complete description of all the assumptions that we have to impose on preferences to be able to represent this kind of preference ordering with a utility function that we would say, right, utility from consuming good one and good two. For our purposes, we don't really care about the assumptions that we need to go from a preference ordering to having a utility representation, because we're going to mostly work in our class here and in most economics classes with a utility representation of those set of preferences. And so when we have preferences over x1 and x2, in this case, we could imagine drawing all the combinations of x1 and x2 that make us equally well off and equally happy. And so we can draw those and say x2 and x1 space, and we call kind of all the combinations of x1 and x2 that make us equally happy. We'll call that gives us, all the combinations of x1 and x2 that make us equally happy and say give us some utility level, we'll call u bar. In this this curve that we've drawn here is called an indifference curve, and it's just that. It kind of tells us all those combinations we're indifferent to for a given level of utility. And we can have multiple indifference curves that all represent different levels of utility. So like maybe this first indifference curve we have was U0, and we have U1, U2, and U3. And we generally, kind of as we're marching out to consecutively higher indifference curves, we're getting happier and happier with those combinations. So our utility that's being represented there is higher. The last bit of the utility function problem that we need to make sure we know about and can talk about would be we want a language to describe the slope of an indifference curve. Right? What's the slope of an indifference curve? It's going to tell us if I take away, say, a little bit of x1, how much more x2 do I need to have to keep my utility constant? So that's the way I'm willing to substitute from x1 to x2, or what we call the marginal rate of substitution, MRS. And so as you can see on any indifference curve, the marginal rate of substitution, the slope of the indifference curve, will depend on where on the indifference curve you're located. Each of these different spots that I've drawn marginal rates of substitutions on are different marginal rates of substitution. And that makes sense because when you have, say, a lot of x1, given that we have preferences to have a bit of x1 and a bit of x2, you're going to be willing to give up a fair amount of x1 if you have a lot of it to get just a little bit of x2. And likewise, if you're on the other end, if If you have a lot of X2, you're going to be willing to give up a lot of that to get a little more X1, assuming you have preferences to kind of have some of X1 and X2. Usually we'll assume that consumers want to have a combination of X1 and X2. But there are a couple of extreme cases that it's worth knowing how to represent. One type of preferences might be that you always want to consume, X1 and X2 in a constant ratio. You might think like tires, right? You always want to have 4 tires per car. Adding a 5th tire with 1 car is not going to give you much utility. Likewise, adding 1 car if you only have 4 wheels isn't going to give you much utility. So the way that we represent preferences where people want to consume goods in a fixed ratio is, essentially to draw it such that your indifference curves don't give you any extra utility if you have more of one of the good or more of the other good beyond that ratio. So they're going to end up, our indifference curves will end up looking something like, this, like L's. And so you sort of see, like if you're at this point with maybe 1 car, 4 tires, adding extra tires keeps you on that same indifference curve. Likewise, adding extra cars keeps you on that same indifference curve. And with these perfect complements, we have that same property of, as you go to higher, I failed in that drawing. Sorry, it should be more like, there we go. As you go to higher levels of indifference curves, you're getting higher and higher utility. You're consuming, more of cars and tires and so on. The other extreme would be perfect substitutes. And with perfect substitutes, your indifference curves will be represented by lines. And the slope of that line just tells you at what rate are you willing to give up good 1 to get some more of good 2 and keep your utility constant. The slope can be 1, but it doesn't need to be 1. And the key bit here is that at whatever fixed rate you have, you're willing to substitute good 1 for good 2, and it doesn't vary with how much good 1 you have or how much good 2 you have. So I think that's the basic first part of consumer choice that you need to have in your pocket, right? You need to know an indifference curve. That's all the combinations of good 1 and good 2. They give you the same utility. We typically will assume non-satiation, meaning that you always get utility from consuming a little bit more of each, but actually when preferences are represented by perfect substitutes, which is that L-shaped pattern, adding more of one good doesn't actually get you to higher utility if you're fixed the quantity of the other good. So that would be an example where a non-satiation doesn't hold. Generally, we think non-satiation holds. Aside from that perfect substitute situation, and so more of each good leaves you better off. Perfect complements are the other extreme from perfect substitutes, where you want to substitute good 1 for good 2 in a fixed amount and doesn't vary with how much of good 1 or good 2 you're consuming. And then lastly, the kind of key word that's going to be the decision variable in all this, or the slope of the indifference curve. That's the marginal rate of substitution. And aside from with the perfect complements case and the perfect substitutes case where it's undefined, marginal rates of substitution will vary with your consumption of good 1 and good 2. So that your willingness as a consumer to substitute between one good and another will depend on how much of each good that you're consuming. The other side of your consumer problem is your budget, right? Your preferences, which are represented by a utility function, tell us how much happiness you get from consuming goods. Your budget tells us how much you can afford. So typically, We'll have a budget that's of the form of the price of good 1 plus the amount of good 1 you consume plus the price of good 2 times the amount of good 2 you consume. Let's notice that's total spending on good 1 and total spending on good 2 equals the income that you're given, y. And since we're representing this in good 2 space, we can just simply write this equivalently as the amount of x2 you're consuming is equal to your income divided by cost of good 2 minus your consumption of good 1 divided by the price of good 2. And so that's just your budget constraint, which we can draw on this x2, x1 space. Notice that it's a line in x1 with a slope of minus p1 over p2, which we call relative prices, which we call the marginal rate of transformation. It's how you're able to transform a little less good 1 into more good 2. Now we're ready to solve the consumer's problem, which is how much of good 1 and good 2 the consumer is choosing. And it's always useful when you begin to solve any kind of problem in economics to ask yourself what's given and what's being chosen. The things that are given, we call those exogenous variables. Things that are being chosen, we call endogenous variables. And in this instance, what are we given? Well, we're given our utility function. We're given the price of good 1, the price of good 2, and we're given our income. So what are we choosing? We're choosing the arguments of our utility function. We're choosing x1 and x2, which are also, of course, in our budget constraint. So let's begin to solve this problem by noticing that given the fixed nature of our budget constraint, which is we only have y income, if I pick good 1 or I pick good 2, then the amount of the other good that I'm going to consume follows directly from that, so long as there's non-satiation in preferences. So I always want to consume as much of each good as I possibly can, which means my budget constraint will always hold with equality. And in that instance, I will basically have the amount of one good completely defined once I choose the other. So I really have a problem of only one variable to choose. So I rearrange my budget constraint, plug that into my objective function that I'm trying to maximize, which is my utility. And so my problem becomes to maximize utility, which is a function of x1, and a function of x2, which is really just y divided by p2 minus p1, p2, x1, and I maximize that by choosing x1. How do I maximize this function of one variable? I'm going to just differentiate it with respect to the single thing I'm choosing, x1, set that first derivative equal to 0, which is a necessary condition for maximum. And so I've got marginal utility from consuming more x1 minus p1, p2 times the marginal utility from consuming more x2 is equal to 0. Rearranging, we get minus p1 over p2 is equal to minus marginal utility from good 1 divided by the marginal utility from good 2. This should look familiar. This P1 over P2, that's the slope of our budget constraint, aka the marginal rate of transformation between goods, which is driven by their relative prices. And what do we have on the right side here? Well, that's how marginal utility changes as we take away a little bit of good 2, and add a little bit more of good 1, otherwise known as the slope of the indifference curve, otherwise known as our marginal rate of substitution. Graphically, we can just draw this consumer choice problem. Draw your budget constraint. Remember that budget constraint is x2 is equal to y divided by p2 minus p1 over p2 times x1. And so the slope here, that minus p1 over p2 is your marginal rate of transformation. And just labeling things here to make it simpler. When x1 is 0, this point would be y divided by p2. Likewise, when x2 is 0, we have the other intercept, which is y divided by p1. So that's your budget curve. How do you make choices? Well, you're going to maximize utility. So you want to choose x1 and x2 to get you the highest indifference curve you can possibly reach. So that's going to be the indifference curve that's just tangent to the budget constraint. So maybe draw one here. That's a given level of utility. All the combinations of x1 and x2 that give you that same level of utility. And so since the highest indifference curve you can get to is the one that's just tangent to your budget constraint, what's the slope of the budget constraint? It's minus p1 over p2, remember? So the slope of your indifference curve then is going to be, which remember is the marginal rate of substitution, is going to be exactly equal to the slope of the budget curve at the optimum, which we just proved using calculus a second ago, but that same thing follows graphically. And that just gives you your choice then of x1 star and x2 star. Now we need to go from this individual problem to the market, to market demand. And the way we can do that is let's think about if we change prices, how do consumer decisions change? And let's say that the problem I'm interested in is the market demand for good 1. So what I'll do conceptually is I'll think about, okay, what happens to the consumer problem if I lower the price of good 1? Well, if I lower the price of good 1, that's going to rotate my budget line out. And what my preferences look like, I think that's another higher level of utility. Call that U, lower. And then what choice do I make in the event that the price of the good 1 goes up? Well, that will just rotate us down, Y, P, high. And then what's the choice I'm going to make? Well, it depends again on my preferences. Looks something like that maybe. U with the high price, where my utility is much lower because it's now more expensive to buy the goods that I want. And so now I kind of have these 3 individual choices at 3 different prices. And I can use that to draw a nice demand curve For an individual, we typically like to draw demand curves and with price on the y-axis and quantity on the x-axis. And so here we can see we've got a very high price, we'll call that pH, where they don't consume very much. Maybe go right here. Then we have that original price, we'll call that P0, where they're consuming more. And then we've got that kind of low price, where they're consuming even more of the good. So we wind up with that nice downward sloping demand curve. It doesn't actually have to be a line. We typically draw it as lines. How do we go from the individual to the market? Well, we just add everyone up. So it's going to have the same shape if everyone's identical. So our market demand curve will look just like our individual demand curve, just with the x-axis scaled differently. Maybe I should draw that separately then. So we'll go with P1, X1. There's our demand curve. Oops. There's our demand curve. And then market equilibrium comes about where supply is equal to demand, and that gives us some equilibrium quantity of good one and equilibrium price of good one. And I have 3 suggested exercises for you just to play around with this model to make sure you're feeling good about it before you step on to the next video. Why not derive the demand curve for good 2 through changing the price of good 2, fixing the price of good 1. Why don't you derive pictures of how much people will consume of good 1 and good 2 as their income changes. And finally, you could derive a cross-price demand curve, meaning like how does my demand for good 1 vary with, say, changes in the price of good 2. You can kind of plot that cross-price demand curve as well. We don't work with those too much here, but it's a good exercise to make sure you're comfortable playing with the model.